Consider the following function, which is defined everywhere except at x equals 0. When x is 0, the denominator is 0, so we could have a vertical asymptote. Let's compute the two one-sided limits as x approaches 0. Evaluating directly, we get the indeterminate form 0 divided by 0. Seeing a square root, we can think about multiplying the top and bottom by the conjugate to see if that simplifies matters. Product of conjugates gives you a difference of two squares in the numerator. Squaring the square root gets rid of the square root. The constants in the numerator subtract to 0. We simplify x squared divided by x cubed, and we are ready to evaluate this limit. So we get a negative non-zero value divided by a denominator that goes to 0 from the negative side. So the resulting limit is positive infinity. Without doing any further work, we can conclude that x equals 0 is a vertical asymptote of f, because at least one of the one-sided limits is an infinite limit. Let's also compute the right-sided limit. We would do the exact same algebra as before. The only difference would be the last step when we evaluate the limit. We get negative 1 divided by a denominator that is approaching 0 from the positive side of the number line, so we get negative infinity for the limit. Consider this function, whose domain is all real numbers x except the ones that would make the denominator 0. Factoring the denominator, we see that the domain is all real numbers except 0 and negative 3. We anticipate that we can evaluate the limit of our function directly by taking advantage of the special trig limit. Seeing how the limit of the two individual factors exist, we can find the limit of the factors and multiply the results. Evaluating directly, we get that the limit is negative 1. Next, let's try to find the limit of our function as x approaches negative 3. Evaluating directly, we get some non-zero number divided by something that approaches 0. So we're going to get some plus or minus infinity and a vertical asymptote, so we better investigate the one-sided limits. Let x approach negative 3 from the left-hand side. Let's consider the factor x plus 3. Since x is to the left of negative 3, x is smaller than negative 3. Adding 3 to both sides of the inequality, we get that x plus 3 is less than 0. We might as well have chosen a test value to the left of negative 3. So suppose that x equals negative 3.1. Plug in the test value into the factor x plus 3 to get a negative 0.1. So the limit of our function is the limit of a function whose denominator is approaching 0 from the negative side. Next, consider the numerator, in particular sine of negative 3. Negative 3 is between negative pi and 0. From the graph of sine, we see that sine is negative at negative 3. Hence, we get a negative numerator and a denominator that goes to 0 from the negative side, so our limit is positive infinity. Next, we let x approach negative 3 from the right. Nothing really changes in the problem, except that the factor x plus 3 is now going to be positive. So the numerator still goes to a negative number, but the denominator is approaching 0 from the positive side this time. So our limit is negative infinity. So in summary, the limit of our function as x goes to 0 is negative 1, so there is no vertical asymptote at x equals 0. However, since at least one of the two one-sided limits as x approaches negative 3 is infinite, we do have a vertical asymptote x equals negative 3. Consider the following function, which is defined everywhere except where the denominator is 0. Setting the denominator equal to 0, we get that x equals natural log of 3. The domain of our function is all real numbers not equal to log 3. Since the numerator of our function evaluated at log 3 is not 0, but the denominator of the function is, we're going to get a vertical asymptote. Before computing the one-sided limit, we'll investigate the behavior of the numerator and denominator. Let's start with the numerator, x minus 1. From the graph of y equals log x, we see that log of 3 is bigger than 1. Since log of 3 is bigger than 1, after subtracting 1 from both sides of the inequality, we see that natural log of 3 minus 1 is a positive quantity. We could have discovered this fact purely algebraically. If we approximate e by 2.72, we see that 3 is greater than e. Take the natural log of both sides of the inequality. Log is an increasing function, so the order remains unchanged. Log of e equals 1, so we see that log of 3 is greater than 1. We can next look at the denominator. Suppose x is approaching log 3 from the left. Then x is smaller than log 3. We can exponentiate both sides of the inequality. The exponential function is increasing, so the order remains the same. And we can subtract 3 from both sides of the inequality to get that e to the x minus 3 is going to be less than 0. Using a similar algebraic or geometric argument, as x approaches log 3 from the right, the denominator of our function is going to be positive. We can now easily calculate the infinite limits. The numerator goes to log 3 minus 1, which we found was positive. The denominator goes to 0 from the negative side. Positive number divided by a negative 0, so to speak, gives us negative infinity. Letting x approach log of 3 from the right-hand side, we again get a positive numerator, and the denominator goes to 0, but from the positive side this time. So we get positive infinity. X equals log 3 as a vertical asymptote of f, since at least one of the one-sided limits was infinite. Consider the function e to the 1 over x. The domain is all real numbers except 0. Let's compute the one-sided limits as x approaches 0. Let x approach 0 from the left. From the graph of y equals 1 over x, we see that as the x approaches 0 from the left, 1 over x tends towards negative infinity. Let u equal 1 over x. And from the graph of y equals e to the u, we see that as u goes to negative infinity, e to the u approaches 0. So we compose those two limiting processes, and we see that as x goes to 0 from the left, e to the 1 over x goes to 0. So now we let x approach 0 from the right. As x approaches 0 from the positive side, 1 over x tends towards positive infinity. And then if u is 1 over x, and u goes to positive infinity, then we see that e to the u goes off to positive infinity as well. Composing those two limiting processes, we conclude that as x goes to 0 from the right, e to the 1 over x tends to positive infinity. We can also conclude that x equals 0 is a vertical asymptote of our function, because at least one of the one-sided limits is infinite. In the next block, we consider the important matter of the continuity of a function.